This is a revision video for P4F, the change in nucleus and radiation around us. All atoms have an atomic number and a mass number. The atomic number is the number of protons in the atom. All atoms of the same element have the same number of protons, and so the atomic number. For example, all carbon atoms contain 6 protons. The mass number refers to the number of protons plus the number of neutrons. A carbon-12 nucleus contains 6 protons and 6 neutrons, or 12 particles in total. When a nucleus breaks down during radioactive decay, this changes the makeup of the nucleus. This leads to the change in the atomic number, the mass number, or both. If the atomic number changes, then a new element is created because of the different numbers of protons in that element. An alpha particle is a helium nucleus. It's made up of 2 protons and 2 neutrons. After a nucleus breaks down by emitting an alpha particle, by alpha decay, both the mass number and the atomic number change. So here we've got our unstable nucleus, and then after the decay we've got the new nucleus, which has now lost 2 protons and 2 neutrons. Those 2 protons and 2 neutrons are in that alpha particle which is being emitted. The mass number drops by 4 and the atomic number drops by 2. This means the element changes. For example, uranium here, 235, becomes thorium-231 after emitting an alpha particle. Okay, so the mass number's gone down by 4 and the atomic number's gone down by 2. Remember, it's the atomic number or the proton number that makes the element the element. In beta decay, a neutron inside the nucleus breaks up into a proton and a beta particle, remembering that a beta particle is a high-speed electron. The nucleus has then lost 1 neutron but gained 1 proton. As a result, the mass number of the atom stays the same. The atomic number, however, goes up by 1 because we've gained 1 more proton. As with alpha decay, a new element has been formed when the atomic number changes. So with our decay equation for beta decay, you can see that the mass number has stayed the same, and because one of the neutrons here has turned into a proton, it means that the proton number has gone up by 1. And because we have to balance both sides of the equation, this is where the -1 comes from on our beta particle. So its mass number is 0. So 231 add 0 is 231, so the top bit balance is fine. But here we've got 90 and 91. So the only way to make this side add up to 90 again is to -1. So with beta decay, remember that your proton number needs to be -1. With gamma decay, the nucleus emits a high-frequency electromagnetic wave. This gamma ray has no mass and no charge, so it has no effect on the mass number or the atomic number of the nucleus. The element stays the same. Gamma decay is often associated with the other 2 types of decay, alpha and beta. The radiation around us every day is called background radiation. It comes from a variety of sources, such as hospitals, nuclear weapons testing, or from nuclear power, including the radiation released in accidents. However, most of it occurs naturally due to the breakdown of radioactive atoms within rocks. Less than 15% comes from man-made activities. Your exposure to radiation depends on where you live and, for example, the nature of your job. Different parts of the country have different levels of background radiation, and an airline pilot or someone working in a hospital can receive a higher dose than other people. This pie chart shows us a breakdown of the percentages of sources of background radiation. We can see that here, half of the background radiation is coming from radon gas or rocks, You've got 11.5% from the food and drink that you consume, 14% comes from the ground and the buildings, 10% from cosmic rays, which come from outer space, and then the remaining last little bit comes from the artificial sources and other sources. Now within the artificial sources, 14% of that comes down to medical uses. We have already looked into some of the uses of ionizing radiation. You may remember that a source of alpha radiation is used in smoke alarms. When smoke enters the alarm, it stops the alpha particles ionizing the air. This leads to a drop in current and the alarm sounds. As well as their medical applications, radioactive traces may be used to map out the path of underground pipes or to track how material is dispersed when it enters the water supply. Radiation can even be used to find blockages or cracks in pipes very deep underground. In order to find the source of a leak within a pipe, a source of radiation is mixed into the fluid flowing through the pipe. A worker can then detect radiation at the surface. If there is a blockage or a leak, the activity detected after the leak will fall. This allows the worker on the surface to pinpoint where to dig. The source used must emit gamma radiation, as alpha or beta particles would not reach the detector above. Radioactive atoms within a substance decay with time. This process can be used to determine the age of rocks or ancient materials using a method called radioactive dating. Scientists take careful measurements of the amount of carbon in ancient objects such as clothing, bones or wooden machinery. This can be used in carbon dating to precisely determine the age of the object. However, the object must be organic. Carbon dating relies on the amount of carbon-14 in the air not having changed for thousands of years. Carbon dating only works with organic material such as wood, cotton or bone. When an organism is living, it continuously absorbs more carbon-14 through biological processes such as gaseous exchange. However, when the organism dies, no new carbon-14 is absorbed, and so, as the carbon-14 atoms decay, the amount found in the material drops. The amount of carbon-14 in the sample is compared to the amount found in living things to determine the age of the sample. You can see from the graph that the number of carbon-14 atoms decays as time goes along. So if you compare the number of 14 carbon atoms at point A to what you would expect that material to have when it was living, then you can find out the age or the time it has been since that organism died. A similar technique is used to date rocks by studying the ratio of uranium atoms to lead atoms. As a rock ages, the uranium inside it decays, eventually ending up as lead. Over the time, the number of uranium atoms decreases as the number of lead atoms increases. The older the rock, the lower the ratio of uranium to lead. Now you have to use uranium to date rocks because rocks are very, very, very old, and carbon-14's half-life is not nearly as long enough to be able to date them. Okay, so that brings an end to this revision section on the changing nucleus and radiation around us.